discussion of titration. So this is a continuation of example 2, where we titrate a weak acid with a strong base. Okay, so in the last one, we saw that by titrating a weak acid with a strong base at equivalence points, the solution becomes very basic because we have a strong base. So now what we're going to do is going to find the pH after 40 milliliters of the sodium hydroxide are added. So again, the first step, we're going to find the initial concentration, the initial moles actually, of the acetic acid and the OH. So again, the mole acetic acid is 0.03 liters, that's what's given, over the 0.5 molarity. Right? So multiply by 0.5 molarity is equal to 0.015 moles. That's how many moles of acetic acid they have. So we want to find out how many moles of NaOH is added to solution. So we have 0.04 liters, okay, because we want 40 milliliters of NaOH solution at 0.5 molarity. So we know that we added 0.02 molar, 0.20 mole of NaOH, which is the same thing as adding 0.02 mole of OH. So then we're going to find the all the things we need using an ice chart. So again, acetic acid is going to react with the water. This H is going to transfer over to become acetate and water. Okay? So here we have the acetic acid as 0.15 molar. The OH now is going to be 0.02 mole. We don't know how many acetate we're going to create, and water is a liquid, so we're not going to worry about it. So here we're going to subtract 0.015 molar because this is going to be the limiting. Okay, the acetic acid is going to be limiting, so it's going to cancel out. So now we have basically 0.05 moles of hydroxide that is left over, and we create 0.015 molar of acetate. So now we need to find the concentration of the OH minus. Now remember, we just added 40 milliliters to a 30 milliliters, so we have to add that up to create a new volume so we can find the new molarity. Right? So we have 0.005 divided by 0.07 because why? Because 30 milliliters of the acetic acid were added to 40 milliliters of the sodium hydroxide. So the water, the amount of water in there, volume actually, is basically add up to 0.7. So we know that the concentration of OH is 0.007. So because we know the concentration of the OH is 0.007, we can find the concentration of the pOH, right? The pOH is going to be negative log of 0.007, which is 1.2. And from the pOH, we take 14, subtract the pOH, we should find the pH. So notice that in this one, the pH is now very high, which means very basic, because at this point, we already used up all the acetic acid. There's no more left. So all the pH now is all the OH now that's causing it. So here is the weak acid strong base titration curve. Notice that there's a certain point where there is a very little change as you add more and more. Okay, so this is called a buffer zone. So this is where a buffer was being created. Okay, but again, you see the same drastic increase and then of course a curving out. So again, at pH of 9 something here is the equivalence point. Remember, it's not the same as a strong acid and strong base, because in a strong acid and strong base you create water and nothing else. But in a weak acid and strong base, you create an acetate, which is a strong base. So which they want to do is pull the electrons off of water to create more hydroxide. Okay, so here the equivalence point is actually at a pH of 9 something and not the 7 like in a strong acid and strong base. So how acid-base indicator work? Now when we do titration, we use a acid-base indicator. It's just a solution that will change color in a acid or basic condition. All right. So acid indicators, acid-base indicator or weak acid. They tend to be weak acid. So in the H, okay, that H is the acid H, right? In an indicator, it is one color. But when we pull that H off, it will change to a different color. Okay. So an acid indicator, acid-base indicator will be an acidic solution that is one color. Then as you acidify it, it will change the color into another color. Okay. So if we have a high acidic situation, right, so there's more H plus, then this equation is going to shift this way, so you have this red color. But if you have high concentration of the acid, it's going to shift to the right, producing this color. And that's how a acid-base indicator works, right? So how acid indicator work is in a titration, there's a large shift in pH. Now notice, remember the graph? There's a big shift in pH, basically at close to the equivalence point. So you got this big shift, and you got this big shift, it's going to cause a drastic color change, and that's why we use indicators. Now, not all indicators can be used because you have to know where the equivalence point is to determine the indicator you want to use. So, for example, if you use an indicator that indicates the pH of 7 and the equivalence point is pH of 9 something, it's not going to work. So you have to pick the right indicator. So how do you choose the indicator? Well, if you know the pH range, you should be able to pick the indicator. So if you think the pH range that the equivalence point is going to be around 7, so brothymal blue should be your indicator. But if you know that it's going to be a little higher, like 9 something, like these weak acid, strong base, then we want to use phenolphthalein. That gives us a more change between those pH scales. So you need to know what the pH range is that you're going to have an equivalence point, and you have to figure out which pH indicator you're going to use for that. Okay, so how do you choose an indicator? What indicator should you use when you titrate HCl with NaOH? Now remember, HCl is a strong acid, NaOH is a strong base, and because you have strong acid and strong base, the equivalent point is going to be exactly 7. Because why? Because strong acid is going to produce H+, and sodium hydroxide is going to produce OH-. So if you look at this graph, you see that there's the equivalence point at 7. So brothymal blue is going to be yellow if it's underneath that, and it's going to start to turn blue when it's above the pH of 7. All right. So what indicator would you use when you titrate 0.5 molar of acetic acid with sodium hydroxide? Now remember, we did that before, and we found the equivalence points of this pH to be 9.1. So we need to find an indicator that has a pH range in that 9.1. So here's the indicator. Phenolphthalein works well. So phenolphthalein around 9.1 will still be clear, and once it passed that 9.1 a little bit, it's going to turn pink really fast. Okay, and we see that. So phenolphthalein will work good with a strong acid and a weak base. A strong base and a weak acid, because remember, the ending solution will probably be more basic. Okay. So choose an indicator. Sometimes only the pKa value of the indicator is given. Okay, so if they give you the pKa value, right, then you know what the pH is. Because remember, the pKa of the indicator will roughly equal the pH at equivalence point. So that's how you know which indicator to use.